Okay, so for the first one, this is a calculator one, and I think we'll use a calculator for every part also. Okay, so they say for time t between 0 and 10, water is flowing into a small tub at a rate given by the function f, defined by that, f of t equals arctan of pi over 2 minus t over 10. For time when t is between 5 and 10, water is leaking from the tub at a rate given by the function L. That's defined like that, little polynomial. Both f of t and L of t are measured in cubic feet per minute, and t is measured in minutes. Okay, the volume of the water in the tub in cubic feet at time t minutes is given by Wt. Okay. So, okay. So I would just, before we start, just kind of realize what's going on here. So they have some kind of small tub here. Okay, and there's kind of water in this tub, water level. There's all this water here. Okay, and then there's water that's going into the tub. And the function that dictates the rate that water is going into the tub is the f of t. And then there's water leaving the tub. And the rate that the water is leaving the tub, leaking from the tub, is given by L of t. Okay, so just little things, how some of these questions work. So the amount, and then the amount of water in here is given by W of t. So just when you talk just amount of water, this is Wt. Okay, so this water level could be rising or could be falling. There's a certain volume, maybe initially or at different points of time, there's different amounts of water in here. But this volume of water in this tub might be increasing or decreasing depending on if water's flowing in or leaking out faster. Right, so whenever this function is bigger than this function, whenever f is greater than L, the water in this tub will be decreasing, kind of the total volume will be decreasing. And then whenever f is bigger than L, the total water in here will be increasing. So, all right, so that's just kind of an overview of what's happening in this problem. Okay, so for A, they say at time t equals 3, just some given point in time, there are 2.5 cubic feet of water in the tub. Let's just write what that is. So that tells you the amount of water in the tub, so that's W. So that's W at 3 equals 2.5. Okay, they say write equation for the local linear approximation of W at t equals 3 and use it to approximate the volume of water in the tub at t equals 3.5. Okay, so just in general, for whatever function you're trying to find the linear approximation of, so here we're trying to find the linear approximation of W. So we'll say the linear approximation we'll say L of t is the slope, which is derivative of W, times, and this is, actually here, sorry, and this is at t equals 3. So we're finding this L of t is specific to a certain point in time, in this case when t equals 3. So that's the slope at 3. And this will just be t minus 3, and then plus W at 3. Okay, and all this is point slope form, right? This is like y. If this W3 was on the other side, this would be y minus y1 equals m, right? Derivative's m, and then x minus x1. Okay, and then now we're going to use this to approximate. So this function here, approximates w around t equals 3. So we're going to use this to approximate w at 3.5, and that makes sense because 3.5 is close to 3. Okay, so that's what we'll do next. So we'll do L of, this will be 3.5 equals, we'll just write this like this for now. Oh, okay, and then W of 3, so think about W3 represents how fast the volume of water is changing of W, of this tub, right? Because W represents the volume of water, so W prime will be the rate that the volume of water is changing in the tub. Since at t equals 3, they give you these range of t values that the functions apply for. So water's just flowing in, but not leaking for the first 5 seconds. It's not until t equals 5 that the water starts leaking. So for the first, from 0 to 5, water's just flowing in, but not leaking. So that means that means for the first 5 seconds, or first 5 minutes, W prime is equal to F prime. Because the only thing that's dictating the water changing is the fact that water's flowing into it. Okay, and then we'll plug in 3.5 for t. Okay. And then now we can go to the calculator. Okay, so good idea whenever you're given these scaffolded FRQs especially, and they give you a couple different functions. So let's go look down to the calculator. I think first thing to do is always just put the functions in there. So arctan is same as tan inverse. You can kind of pause and see if you want to see how I get fractions, you can see the buttons that get pressed. Whoops. Alpha and the button to the right creates a fraction. Okay, so that's F of t. It's the rate that water's flowing into the tub. Okay, so this is L of t, rate that water's flowing out of the tub. Okay, so now we're just going to kind of go back to a blank screen and just kind of do this. So now, yeah, let's get y1. Remember, y1 is really f prime. So remember, now we're going to plug in 3 into f prime, just like our formula says. And then times, we'll do 3.5 minus 3. So we're just really typing in exactly what we've already figured out. And then W of 3, they tell us, is 2.5. They say it in the problem. And so that's it. So that's our answer. Okay, and then using units, we're approximating W, so our units are going to be the same units as W, and they say W here is the volume and measured in cubic feet. Okay, so that's the answer to part A. Okay, next one. So now they talk about how they want us to find the second derivative of W. And now they want us to find it at 8, so a different x value, and that actually matters. The fact that the first one was at t equals 3, there's kind of different things going on at 8 than there were at 3, so we'll see in a second. So they say using correct units, interpret the meaning of the second derivative of w at 8 in the context of this problem. So we'll find the second derivative of w at 8 and then interpret its meaning. Okay, so first thing is that w prime, so if we think about just w prime, just the first derivative of w, so that represents the rate that the volume of water in the tub is changing, right? Because w represents the volume of the water, so w prime will be the rate that the volume of the water is changing. Okay, notice that is just given by f of x, or f of t. That should be a t. That should be a t there. I'm going to fix that. Okay, so notice they already gave us f and l as rate functions. So if you take the rate that water's going in and subtract the rate that water's coming out, if you subtract those, that's kind of the net rate that the volume of water is changing. Okay, so we realize, really, let's write that. Actually, let's write that first. So w prime of t equals just regular f of t minus regular L of t, no derivatives. Okay, so that's a little tricky, realizing a derivative equals functions that aren't written as derivatives, don't have the prime notation. Okay, now we can take second derivative of both sides, so w double prime of t equals, and now just, when you're taking derivative of both sides, just take derivative of each term separately. Derivatives distribute to things added or subtracted. Okay. Okay, and then now if we want w double prime at 8, second derivative of w at 8, that's really just derivative of f at 8 minus derivative of L at 8. Okay, so let's find that in the calculator and then we'll interpret it after that. So there's different ways to do this. You could actually make a whole new function like into y3 and call that y1 minus y2, and that would be w prime. But here I'm just going to kind of put subtract y1 and y2, so that'll be the derivative of each of those, and then just find that at 8, and that's it. Okay, so that equals, oops, negative, oops, 0.183. Okay, and this is the second derivative, so this would be second derivative of w, which is derivative of f and l. So f and l, let's say units are cubic feet per minute, and so when you take a second derivative, it'll be cubic feet per minute squared. Okay, and then to interpret it, you'll say something like, you can say it in different ways, but you'll say, you talk about at an instant, because this is all happening at t equals 8. Here, let me see how they read. Yeah, we can just say at t equals 8. They don't say like, t represents the time since the water first started flowing into the tub. I guess you could say that. So you could say, whoops. You could say something like 8 minutes after water you could say the rate of change, the volume, the tub. Say something about how that rate of change was decreasing. Since it's negative, rate of change of the volume of the water in the tub was decreasing. So notice we're talking about the rate decreasing. Right? The rate decreasing by 1 point, or whoops. Cubic feet per minute squared. Yeah, so 8 minutes after water started flowing into the tub, the rate of change of the volume of water in the tub was decreasing. The rate was decreasing by that. Okay, so part C says, is there a time t between 5 and 10 at which the rate of change of the volume of water in the tub changes from positive to negative? Okay, give a reason for your answer. Okay, you can do this different ways. You can actually give the intervals where it's positive and negative, and then see, if this is a continuous function, which this is going to be, the function that we look at. If it's continuous, it'll be 0 at the point where it changes from positive to negative. So that's one way. I kind of did it a different way. I'm going to use intermediate value theorem, just for no good reason. You can do it completely either way. It doesn't matter. So, and I'll show that. I'll kind of talk about that once we pull it up on the calculator too. So, makes no difference at all. So, okay. So they say, is there a time t at which the rate of change of the volume of the water in the tub changes from positive to negative? So the rate of change of the volume, we're looking at the rate of change of the volume of the water. Okay, so the rate of change of the volume of the water for us is f of t minus L of t. Right, each of those are rates of change of the water. This is the rate that it's flowing in. This is the rate that it's leaking out. So the difference of that is just the rate of change of the actual volume of water in the tub. Okay, so we want to know, is there a point that this function, which is really the subtraction of two functions, but really this is a function on its own. And so is there a point, is there a time on this interval from 5 to 10 where this function changes from positive to negative? Okay, so I'm going to do this. I'll look down in the calculator. So I could have done this earlier, but I'm going to unhighlight these equal signs because I don't want to actually graph these, but I do want to graph the difference of these. So that's y1 minus y2. so notice what this is here. So this y1 minus y2, so remember y1 was f of t and y2 was L of t, so y1 minus y2 is this exact function, f of t minus L of t. So we want to see when this changed on this interval from 5 to 10, if this changed from positive to negative at some point in time on that interval. So it makes sense to graph it, but also makes sense to change the window. So let's go to a blank screen first. So let's change the window. Let's make that 5 to 10, which I already did, right? And then we just wanted to see when it changed from positive to negative. So we just want to see kind of around, the y min and y max. Just make that negative 2 to 2 or negative 1 to 1. We just kind of want to make sure we include the y-axis to see if it went from above the y-axis to below the y-axis. So we want just a little bit above the y-axis and a little bit below the y-axis. But you could have done negative 10 to 10, doesn't really matter. I'm just kind of focusing on the y-axis just because it kind of makes it just kind of nice to see. So, and then notice I made this 5 to 10 just because that's the interval, so that'll hone on to the interval that hone into the interval that we want to focus on. Okay, so let's graph it. So now we can see, right, it did change from positive to negative. So one way that I was saying earlier that you could do, you could just give, you could calculate the 0, whatever that is. Looks like around 4, maybe. Oh no, this is 5, 6, 7, 8, somewhere around 8, maybe a little more than 8. So you could give the interval that it's positive from 5 to 8 point something, and then give the interval that it's negative 8 point something to 10, and then say that at 8 point whatever it equals 0, and so that's the point that it changed from positive to negative. So you could actually give the point. So what I'm going to do though, I'm going to just into this function, which is really f of t minus L of t, I'm going to plug in some positive number and some negative number, and then we're going to use intermediate value theorem to prove that there has to be a point where it changed from positive to negative. Okay, so we're going to do f of 3 at 5. We know that that's positive from the graph. And then go highlight that and edit it to make that 10. Okay, and that ended up being negative. Okay, so now let's use that. Okay, so first off, each of these functions on their own are continuous on this interval. So, f of t is some kind of arctan, and arctan is going to be continuous on whatever, and really arctan is always continuous. So, and then L of t is like some polynomial function, and polynomial functions are also always continuous. So if you subtract two continuous functions, you're going to get another continuous function. Okay, so this function's continuous, but we have to say that in order to use the intermediate value theorem. And let's actually call this what it is. We know that this is really w prime of t from part B, I think. We'll say since w prime of t is continuous, on the interval that they're talking about, and it really has to be a closed interval, so you have to use brackets. We could say and, okay, then we'll come down to the calculator, and w prime of 5 is positive, and w prime of 10 negative. There must be some t such that Wt equals 0, and this would be the point at which W prime of t, oops, it should be W prime of t, sorry, W prime of t, point at which W prime of t would change from positive to negative. Alright, and there's tons of ways to say that. That's just one way. And I don't know. A bunch of other ways, I'm sure. Okay, so next one. Part D. Okay, the tub is in the shape of a rectangular box that is 0.5 foot wide, 4 feet long, and 3 feet deep. Okay, what's the rate of change of the depth of the water in the tub at t equals 6? Okay, for part D, they say the tub is in the shape of a rectangular box. Yeah, actually, sorry, I just had to pause. I forgot I already read that. Okay. Yeah, what's the rate of change of the depth of water at t equals 6? Okay, so let's say you're drawing a tub that's a rectangle, something like this. So it doesn't have to be to scale or anything. Okay, and then there's water. Who knows? We'll start off water's at a certain depth. Okay, and this is just kind of all filled with water here. Okay. Okay, we don't know what the depth is, but whatever, it is what it is. Okay. And we'll say maybe that's 3, that's 4, and this whole thing is 6, but that's not that important. That 6 isn't important because we are really going to be more interested in the depth of the wall. Oops. Oh my God. Yeah, so we're going to be more interested in the depth of the water than the depth. This depth of the actual tub, this container, is not going to matter because we're more interested in just the water itself rather than the tub. Okay, but the water kind of takes the shape of the tub, so the fact that the tub is rectangular means the water is always going to be rectangular. So, okay, so they want the rate of change of the depth. Okay, so think about this. So the volume, okay, is going to be, let's say, width times length times depth. Okay. But notice when you're doing this, the volume's going to be changing. So the volume's going to be some function of time changing. But the width and the length aren't changing. The width is always 3, and the length is always 4. But then when water flows in, just like the volume's going to change, the depth is the only thing that's going to change. Okay, so D, we can say D is a function of time. Okay, so we know that the rate of change, and this volume for us, I put volume, but this is really W. So we realize this is WT. So we'll call it that. Okay, so now we can take derivative both sides. You know, that's 3 times 4 is 12, so we can write this as W prime of t equals 12 times d of t, d prime of t, sorry. And then the rate of change of the depth is d prime of t. So that means that d prime of t is w prime of t over 12. Okay, and then if they want it at t equals 6, we're basically just going to plug in 6. Okay, so our answer is just going to be whatever. Our answer is going to be, kind of ran out of room, it's really going to be d prime at, let's say d prime of 6, which is really w prime of 6, which we can find easily, over 12. Okay, so let's go to the calculator, do that. Okay, so the fraction, top. y3, remember y3 was w prime of t, 6, and then just divide that by 12. Oh, actually I don't know why I just made a mistake. Okay, that shouldn't have been 12. I don't know why I did that. It's 0.5 feet wide, not 3 feet wide. So this should be a 0.5 here, which will make this a 2. And that's right now. So this should be divided by 2, not 12. So here, let me fix that. And that'll be a 0.5, which will make that a 2, and that a 2. Okay, that's perfect. Okay, so here they give us a piecewise function, wt, and just two different functions, one from 0 to 6 and one from 6 to 10. Okay, the top one includes 6, and the bottom one is not including 6. Okay, so they say the depth of the water at a certain point is modeled by this function w, defined above, where wt is measured in feet and t is measured in hours. So this is the depth of a river. You know, whatever value of t you plug in, which is some hours after something happened. When you plug in t into the appropriate part, you'll get the depth of the water of the river at that t value. Okay, so first one they say find w prime of 8 and then interpret the value in the context of the problem. Okay, let's just find w prime of 8 first. We use correct units and then we'll interpret it after that. Okay, so you know, w prime of t technically would be taking derivative of the top and but we'd take derivative of the top and bottom, but here we're only wanting to know w prime at 8. So since 8 falls into this domain, we'll just use the piece associated with that domain. Okay, so then at least for values between 6 and 10, including 10, w prime of t equals, okay, so the derivative of that, so the derivative, you can do this different ways. So the derivative of 10 is 0, so that'll go away. Okay, and then now we can just do power rule. So we can do the constant times 2, bring this 2 out, multiply it by the -1/5. So it'll be -2/5 times t minus 6, technically to the 1 power. And then there really is no chain rule. Chain rule, if you take derivative of the inside, that's 1, so we don't have to write that. Okay, and then now we just want to evaluate this at 8. So w prime at 8, -2/5 Okay, so W is in feet, T is in time, so this will be, every time you take a derivative, it'll take the units of the function, W, which is in feet, and every time you take a new derivative, it'll divide it by the units of the independent variable, which is T in this case. So this will be in feet per hour. Okay, to interpret this, sometimes you can say 8 hours after something began or something. You can kind of talk about the time in more context. Here, we don't know T is like a certain time after something began or after something happened. T is measured in hours, they say. They don't really talk about what T is, but beyond that. So we can just say at T equals 8. We can talk about the depth, how the depth of the water is changing, and since it's negative, water, might as well say it's decreasing by 4/5 feet per hour. Okay, the fact that you're saying it's decreasing, that really incorporates that negative. So you don't want to say it's decreasing at a negative rate. Decreasing implies that this is negative. So, okay, so something like that. Okay, part B says the graph of W is concave down between 3 and 3.5. Use the tangent line to the graph of W at T equals 3 to show that W at 3.5 is less than 9. Really less than or equal to 9. Okay, so I say let's just find the tangent line approximation. They say use the tangent line of the graph of W. That's really like the linearization concept that we'll use. So use the line tangent of the graph of F to show that W of 3.5 is less than or equal to 9. So we'll really find L of T, the linearization for W at T equals 3, and then use that to approximate, and basically just plug in 3.5. And then after we do that, then I'll kind of explain the concept. But let's do that first. Okay, so here I'll write the general kind of formula or format for linearization. So just in general, L of T or L of X. Okay, whatever function you're trying to approximate, first you'll take the derivative at some T value, some X value, in this case it'll be 3. Always times it by T or X minus that same value, and then add just the Y value of the function at that T value. Okay, for us, in this function, it'd be L of T equals. Okay, and we're approximated at T equals 3, so in the piecewise function, we'll be using the one with cosine above, since that applies for values between 0 and 6, and 3 is in that interval. Okay, so we'll really be doing W prime at 3, T minus 3, plus W at 3. Okay. Actually, let's do some scratch work. So let's do, I'll do that above at the top. Okay, so at least on this top, for this top interval, if we take derivative, I'll just kind of rewrite it. So derivative will be, rewrite the constant. Okay, derivative of cosine is negative sine. Keep the inside the same. Okay, and then chain rule, take the derivative of the inside. Derivative of pi t over 6 is just pi over 6. Okay. And then that equals, we'll kind of clean it up. That'll be positive, since there's 2 negatives, and that will be pi over 4. sine of that. Okay, so if we plug in 3 into that, because we want to find, so this is w prime of t, at least on that interval. So if you plug in 3 into that, this inside of sine, this angle for sine becomes pi over 2. Oh yeah, and then sine of pi over 2 is 1, and then 1 times pi over 4, just pi over 4. Okay, and then w of 3, so we'll plug in 3 into the original now. Not much room, but so w of 3, okay, is 17 over 2 times, okay, and then if you plug in 3 into here, you get cosine pi over 2, and that's 0. Okay, so this just w of 3 just ends up being 17 over 2. Okay, so now let's plug in 3.5. This will be our approximation. So L of 3.5. Okay, so if you think about it, this is just a half, right? 3.5 minus 3 is 0.5, which is a half. And a half times pi over 4 is pi over 8. And then that'll be 17 over 2. I'm going to rewrite that as 68 over 8, just times top and bottom by 4. Do 17 times 4, that's 68. And this will be 68. I'm going to rewrite this as 68 plus pi over 8. Okay, now, so now is going to be the idea that we'll use. So now think about, they say at t equals 3 that this function's concave down. So who knows what exactly, we won't worry about exactly what this function looks like. But at t equals 3, we know it's concave down. Okay, let's say that's at 3. Okay, so who knows what this tangent line is, something like this. But what that means is whatever the value of the tangent line is at 3.5, let's say now we're looking at 3.5 here, some value close. So notice at 3.5 that the approximation is less than, or is greater than, the approximation is greater than the actual value of the function. And that's going to be true anytime a function's concave down. The approximation using the linear approximation, the linearization, is always going to be greater than the actual value of the function. Okay, so now think about this. So they say use a line tangent to show that the actual value of the function is less than 9, right? W of 3.5 is the actual value, and they want us to show that it's less than 9. So think about this. This here is less than 9. Our linearization, which is this value up here, is less than 9. Okay, so and we can tell this is less than 9 because this would equal 9 if the top was 72, right? 72 divided by 8 is equal to 9, and pi is about 3, right? So this is a little more than 3. So this is like 71.14, you know, pi is 3.14, so this is like 71.14. So this is a little less than 9, right? This is, yeah, but definitely less than 9. So now we can say L of 3.5 which is this, equals this, or, sorry, let's do it this way. Actually here, sorry, let me think about the best way to write this. Yeah, so maybe we'll just put like, I'll just put L of 3.5, we know is definitely just less than 9. Okay. And then that actually, no, sorry. Yeah, there's a better way to write this. Oops. Okay, let's write, start out with W. Let's say W of 3.5. Okay, that's our actual value. Is greater than, or sorry, is less than L of 3.5, which we know that is less than 9. And so that's what you need to show, right? If this, inequalities have a transitive property, right? If W of 3.5 is less than L of 3.5, and L of 3.5 is less than L of 9, we can say therefore W of 3.5 we can say is less than 9, but let's just say less than or equal to, because that's what the problem asks us to show. So, okay, yeah, so definitely the actual value is less than the linearization, right? The actual value, because it's the function's concave down, the actual value is less than the linearization, and the linearization is less than 9, right? Because we know it's 8 point something. And so if this inequality holds, then this has to be less than this. So, okay. Okay, last one for this. Let's focus on this. Okay, so they give us a limit. So first thing, let's just plug in the limit, see what happens. We have an idea we're going to get 0 over 0 probably, but let's find out. So this, so plug in 2, let's see what happens. So then W of 2. Okay, T cubed is 8. Okay, we know the bottom is 0. And then W of 2, let's plug in 2. Okay, so if you plug in 2 for T, you get cosine pi over 3. Okay, cosine of pi over 3 is a half. Okay, and then so that'll be 17 over 2 minus, this will be 3/4, because this will be 3 halves times 1 half. Okay. So W2 is 17 over 2 minus 3/4. And that'll be minus 8 plus 1/4. Okay. So we'll get a common denominator on the top of 4. Okay, 17 is 34 over 4 minus 3 over 4 minus 8, which is 32 over 4 plus 1 over 4. And then we can see that does equal 0. The top is 0, so 0 over 4, that's 0 over 0. Okay. Okay, so that means we can use L'Hopital's rule. So that means we'll say, if we're going to show work, we'll say this limit equals limit t approaches 2, and then we'll just take the derivative of the top and bottom separately. So we know the bottom is just going to be 1, right? Derivative of t is 1, derivative minus 2 is 0. So we know that this will be the only time we use L'Hopital's rule, because we're not going to get 0 over 0, we're going to get something over 1. So okay, so let's take derivative. So w prime of t. Okay, derivative of t cubed is 3t squared. Derivative of fourth is 0. Okay, so now we'll plug in 2 into this. That'll be prime of 2. And technically it's over 1. Oh, that'll be the last time I write that. So w of 2. So we'll plug in 2 into the top part of the piecewise function. I'll write down the whole thing. So that'll be 10 over 2. Oh, whoops. Okay, so we already got w prime, which is really, we'll use this one. So we're plugging 2 into this. So plug in 2, you get sine of pi over 3. Okay, sine of pi over 3 is root 3 over 2. So this will be pi over 4 times root 3 over 2. Okay, and then minus 3 times 2 squared, 3 times 4, which is 12. Okay, remember you can leave your answer like this if you want. I'll clean it up just in case it's like a multiple choice question. Okay, and then we get a common denominator, so 12 is 96 over 8. So this will be pi root 3 minus 96 over 8. Okay, so for second FRQ of part B, let's say a particle moves along the x-axis so that its position at time t greater than 0 is given by x of t, which is that rational function t squared minus 9 over 3t squared plus 8. Okay, part A is just one of these ones that are show that. So show that the velocity of the particle at time t is given by v of t equals that. So we know that velocity is the derivative of position. Sorry about the dogs. I don't know. Neighbors aren't doing anything about it, but all right. So we'll take derivative of this, and we should end up with this. Okay, so let's do that. So we got a quotient rule to do. It's going to be longer than that probably, but we'll start off with that. So always start off taking derivative of the top. So derivative of the top is just t squared, because the minus 9 goes to 0. It's 2t. T squared 2t, and then just times the top. Minus, and then rewrite the top. And times the derivative of the bottom. T. And then all over the bottom squared. So we see how they got the bottom squared in the answer. Just from quotient rule. Okay, so now the top must just simplify to be 70t. So let's just confirm that. So we'll distribute the 2. So we'll get a 6t cubed, and then plus 16t. Okay, and then it's going to be a minus 6t cubed, and then really a plus 54t. Okay, this minus will distribute to the 9 to make it a plus 9, and then this 6t will distribute to that. So that'll be a positive. Okay, and then those cancel, and you see how you get that. Okay, these you're just trying to show a reasonable amount of work. You don't want to just start off with this and just equals that right away as if it's obvious. You got to show maybe the first step of the quotient rule, a little bit of simplifying, and then now it's reasonable to show this answer. Okay. that's it. Okay, for part B, they say is the particle moving towards the origin or away from the origin at t equals 2. Okay, so what dictates whether it's moving towards or away from the origin is the position, whether it's positive or negative, and then the velocity, whether it's positive or negative. So just to kind of go over the concept quickly. So this is always talking about a number line. We're talking about it, particles kind of bouncing back and forth on a number line that has an origin to it, right? 0 is the origin. And some particles just going back and forth, you know, who knows, kind of going back and forth, moving, changing directions, right? So there's kind of two possibilities for how this could be moving towards the origin. So here, the particle could be here. Okay, in that case, it's actually, let's do it like this. So particle B could be to the right of the origin. So that means the position would be positive. And then it could be moving to the left. That would be moving to the origin, which would mean the velocity would be negative. That's one possibility of moving towards the origin. Position is positive, velocity is negative. Okay, position positive means it's to the right of the origin. Velocity negative means it's moving to the left. So to the right of the origin, moving left. It could also be to the left of the origin, moving right. Okay, left of the origin would mean the position is 0. Moving right would mean velocity positive. Okay, so those are the two options for moving towards the origin or away from it. Okay, moving away from the origin would just be same kind of concept. Moving away from the origin is if, let's say you have a particle here to the right of the origin, moving to the right of the origin would have a positive position, and moving right would have a positive velocity. Okay, or the particle could be to the left of the origin, moving left. To the left of the origin would be a negative position. Moving left would be a negative velocity. So those are our two options. So basically we're just going to find the position and the velocity of the particle at t equals 2 and look at the signs of each. Okay, so let's look at x of 2 first, maybe position at 2. Okay, so there's our position function up there, so I'm just going to plug in 2. Actually, let me grab that. Okay, there's our position function. We're going to plug in 2 into that. So 2 squared is 4, minus 9, over 3. Yeah, so really, so plug in 2, this ends up being 12 plus 8, that's 20. So whatever this is, you know, this is negative 5 over 20. It doesn't really matter what the value is, just as long as we know that this is negative. Okay, so the position is negative, which means the particle at t equals 2, the particle is to the left of the origin. And then let's look at velocity now. At 2. Okay, we've got our velocity function up here. So plug in 2, the top will be 140. And the bottom's always positive. We can tell the bottom's positive. I'll just plug in 2. So if you plug in 2, this is 12 plus 8, which is 20. Squared is 400. So that's positive. Okay, so now we have the scenario where the position's negative and the velocity is positive. Position negative, velocity is positive, so that's like this situation. And so this particle is moving towards the origin. we'll say something like, give a reason for your answer. All you have to say is since x of 2 is negative and v of 2 is positive, moving toward the origin. Okay, part C says the acceleration of particle is given by a of t. Write an expression for a of t and find the value of a of 2. Okay, so I copied the velocity from the from our previous answer, one from part A, and so we know acceleration is derivative of velocity, so that's what we'll do. So we'll just take derivative of this. Do it in red. So acceleration is derivative velocity. So that's it. So we'll just find derivative velocity and then plug in 2. Is that what they asked for? Right, expression for a of t, yeah, and then find a of 2. So it's kind of two parts. Okay, so we'll do quotient rule. So derivative of the top is just 70 times the bottom minus the top. Times derivative of the bottom, we'll start off with power rule, keep the inside the same to the 1 technically, and then times chain rule, derivative of the inside is just 6t. Okay, so that's an expression for a of t. You know, remember technically you don't have to simplify it all. So I'm going to, just because. So I'm going to show you all too, like how to, kind of the best way to simplify this maybe. So top, you just have 2 terms here. And remember, when you factor out, one way to factor is factor out a GCF, and a GCF is just what's common to both terms. So you know that there's at least a 3t squared plus 8 that's common to both, right? This has 2 3t squared plus 8's multiplied. This at least has 1, so there's 1 that's common to both, and they both have a 70 that's common. Okay, so we'll pull out 70 plus 8. Okay, and then when we factor this out of this, so we're seeing, what are we missing? So we're missing one of these 3t squared plus 8's. And then from the other one, you're pulling out the 70 3t squared plus 8. So we've got the 70 here and the 3t squared plus 8's here. So the only thing we're missing is a t, a 2, a 6, and a t, which is 12t squared. Okay, and this is going to be over the bottom to the 4th power, because it's squared squared. Oh, wait. Oh, I should have been, whoops. So here I made a mistake. So this should be to the 4th right away, because we were trying to, when you do quotient rule, you have to square the bottom. And when you square a square, should be to the 4th. Okay, so you see that should be to the 4th, and then that's to the 4th there. Okay, and then now we'll just simplify what's in the brackets. So 70 times 3t squared plus 8, and then that'll be negative 9t squared plus 8. Okay, and then now we can, just one last step, we can cancel out at least that whole factor, and then that's 3. this. A lot of times you don't want a negative term to come first, if you can help it, but really makes no difference for a free response. So remember, for a free response, you can leave it just like that if you want. I'm doing it just for practice. Okay, so that's the first part where they ask us to write an expression for a of t. So that's a of t. And then they want us to find a of 2 now. So let's do that. Okay, that would just be plugging in 2 into that expression. Okay, if you plug in 2, t squared, 2 squared is 4, times 9 is 36. 8 minus 36 is negative 26. Wait, what am I talking about? Negative 28. All over. And then if you plug in 2 into the bottom, you get 12 plus 8, which is 20. And that'll be 20 cubed, which is really 8,000. Okay, and then that makes no difference how much you want to simplify. I might take a 0 away, and then divide by 4. Divide that by 4, that'll become 7. Divide that by 4, that'll become 200. Okay. This will become negative 49 over 200. Okay, what position does the particle approach as t approaches infinity? Okay, so what they're really asking us to do is to take limit as t approaches infinity of x of t. That's the position. Okay, so position, I'll kind of rewrite this from above. And then this is a quick one. So you could plug in infinity for t, and then get infinity over infinity, and then use L'Hopital's rule. But you can also just use top heavy, bottom heavy, same. And so you could see right away that this just equals 1/3. Okay, and that's it. So I'm gonna do L'Hopital's rule. This will be the last thing I do, just for practice. So the fact that you get infinity over infinity, which is an indeterminate value, that means you can take the limit as t approaches infinity again, and then take the derivative of the top and bottom. So derivative of the top is 2t. The derivative of the bottom is 6t. And then here you can actually just cancel out t's, whoops, and then limit of a constant is just the constant, so now you get 1/3 doing it this way, using L'Hopital's. Okay, but we didn't need to really, because we could just use this idea of like top heavy, bottom heavy, same, which you can use anytime t is approaching infinity or negative infinity for a rational function. Really any kind of fraction, or most fractions. All right, so that's it.